Okay, so you can look at a few questions from gravitation. Using the conservation laws, demonstrate the total mechanical energy of the planet of mass m moving around the sun along ellipse depends only on the semi-major axis. Find this energy as a function of time. So the figure is going to be like this. There is sun and there is earth moving, and let me say this length is r1, this length is r2, then semi-major axis, this total will be r1 plus r2, so semi-major axis will be r1 plus r2 by 2. Now if the speed here is v2 and the speed here is v1, I have taken. Now I can write this one, potential energy at any point plus kinetic energy at any point will be total energy. Now this is generalized for any point on the ellipse, but for these two particular points, what I can do is I can write kinetic energy as L square by 2 times of moment of inertia, L square by 2 times of moment of inertia. That I can write only for these 2 points, because that angle between position vector and velocity is turning out to be 90 for only these 2 points. So for only those 2 points, I can write kinetic energy as L square by 2 times of mr square. L is angular momentum. So the meaning is the roots of this equation must give me these 2 points. It is a function in r, so I will be writing quadratic in r. Now roots r1 plus r2, roots will be minus b by 2a. That must be giving me roots of these two, like which is r1 and which is r2. So this is a quadratic whose roots will be giving me r1 and r2. So sum of the roots will be this much. So total energy will be minus gmm by r1 plus r2, which is minus gmm by 2 times of semi-major axis or minus gmm by major axis, right? Now similarly, a planet of mass m moves again along the ellipse around the sun, so that its maximum and minimum distances from the sun are r1 and r2 respectively. So find the angular momentum of the planet related to the center of the sun. So again I will be drawing the same figure. Now yeah, I have done the same thing. I have done for some generalized position, and I have taken for these 2 particular positions. Only for these 2 particular positions I can write kinetic energy as L square by 2 mr square. So the roots of this equation must give me these 2 particular positions. So I will be writing this equation as a quadratic in 1 by r. So 1 by r1 plus 1 by r2, so that is summation of the roots will turn out to be this much. When I modify it, I will be getting angular momentum is this much. But anyway, so if you want to remember, you can remember this result or you can get it back easily, but you have to remember that energy result. It will be helpful at many places. Now the next question goes like, a small body starts falling into sun from a distance equal to the radius of the sun's radius of the earth's orbit. The initial velocity of the body is equal to 0 in heliocentric reference frame. Make use of Kepler's law. So we will try to do it without using Kepler's law. So what you are trying to do is, there is sun. Earth earlier was rotating in circular motion. Now you stopped the earth and you left it. So initial velocity is 0. Because of the attraction, it will be moving, and it will be hitting the sun. Sun's mass is very large, so we will be assuming that it is not moving. So at particular moment, Earth's speed will be v at a distance r. So I can use energy conservation between these 2 positions. So what I can say, initial total energy equal to final total energy. From here I will be getting v equal to root of gmm by whatever it is. Now what is v? The rate at which this length is reducing. So v equal to minus dr by dt. So from here I need to integrate from where to where? R is initially capital R, finally it is 0. So that's what I need to integrate, but integration is up to you. I did here, but I am not going to explain it. So I just assumed 1 by r equal to secant square theta by r. So you can do it by yourself. When I integrate this, I will be ending up with some result like r root r pi by 2. So this integration will turn out to be r root r pi by 2. The right side will turn out to be this much. So you will be getting the total time as 1 by 4 root 2 times of this much. What is this? This is the actual time period of the earth when it was rotating in circular motion. So it is 1 by 4 root 2 times of actual time period of the earth when it was rotating in circular motion. But we can avoid all these things if we have understood Kepler's laws. So earth was performing circular motion, so when you stopped it and when you leave it, it will be going and hitting the sun. Now what you can do is, you can visualize it as a flattened ellipse, like ellipse whose minor axis is almost 0. But what Kepler's law says, time period doesn't depend on minor axis length, time period depends only on the major axis length. So whether it is this ellipse or this ellipse or this ellipse or some circle, then the time period will be same. So I will be going with this line I am seeing it as ellipse. Now that line motion I am seeing it as ellipse. That's the only thing. So for this ellipse, what is the total time period? That time period square will be proportional to that semi-major axis cube. Semi-major axis is how much? R by 2 whole cube. But what was the time period here? Time period will be proportional to R cube. Time period square will be proportional to R cube. Initially, this is actual time period of Earth. Actual time period of Earth whole square is proportional to this distance whole cube. Now, this time period of this ellipse square is proportional to this semi-major axis whole cube. Now what I need to find this time in terms of old time. So I will be taking the ratio. I will be getting this one. But what we have seen the answer as 1 by 4 root 2. So the meaning is this is not going to be the answer. Why this is not going to be the answer? This is the total time period of full ellipse. But what we need? We need only half ellipse, right? The going and hitting. So only half of it we need. Only half of this one we need, which is going to be t by 4 root 2, which is almost 65 days. So if Earth is stopped and left, it is going to take almost 65 days to hit the sun. The next question goes like, in terms of G, L and masses, what is the rotational period of equal mass double star where the separation is L, then unequal when the separation is L. Then third question is equilateral triangle equal masses, then equilateral triangle unequal masses. So the first one, equal masses, the center of mass will be at the center, the total distance is L, so this is L by 2, this is L by 2, so this will be performing circular motion. Now when this goes here, this will be going here, when this goes here, this will be going here, when this goes here, this will be going here. So by the time it performs one circular motion, this one also will be performing one circular motion, right? So this omega will be same as this omega. The same thing will happen in all the cases also. So omega will be same for anything, so I will be taking for either any one of the objects. So what is the net force on this? G m square by L square. Net force equal to m omega square and into its radius, right? So from here I can find omega, I can find time period, right? So similarly for unequal masses, if I do it, it is going to be a little tricky. So this is m1, this is m2, I will be finding the position of center of mass. If the total distance is L, I can find this distance as m2 into L by m1 plus m2, which I am calling it as r1. And this distance I will be getting it as m1 L by m1 plus m2, which I am calling it as second radius, right? So I can write F equal to ma for any one of the thing. So I will be writing for this object, what is the force on this object? G m1 m2 by this distance square, G m1 m2 by L square equal to m1 omega square times r1. What is r1? r1 is this value. So when you substitute and when you modify, you will be getting time period as 2 pi into root of L cube by G of m1 plus m2. Now you can see it is starting out with the same form, but it's like mass thing is earlier it was 2m, now it is m1 plus m2. Now you can expect that it will become 3m here, it will become m1 plus m2 plus m3 in the next one. Now in equilateral triangle, right? So you need to write center of mass will be here. So it can be like inscribed in a circle, right? So this will be the center of mass. So you need to find what is the net force towards the center equal to m omega square r. Now if I take this particle, the force on this particle in this direction is gm by L square. Because of this one is gmm by L square. So the resultant of this plus this is that f cos 30, which is root 3 into gm square by L square. That is the net force on this particle towards the center. That equal to m omega square times this radius. What is this radius? That is 2/3 of the height. Right? So net force on this particle towards the center equal to m omega square times this radius. From there I will be finding omega, from there I will be finding time. So all this you can do. The only little difficult thing is this one. When there are unequal masses, m1, m2, m3, so I am trying to figure out center of mass first. So I will be trying to write the vector notation with respect to center of mass. So what I can say, if I take this as my origin, m1 r1 bar plus m2 r2 bar plus m3 r3 bar, that must be 0 by definition of center of mass. Now I will be writing force on first particle. Force on first particle is, because of this one is gm1 m2 by L square, along which direction? Along this direction. This direction I can write it as r2 bar minus r1 bar by L. So this direction I can write it as r2 bar minus r1 bar by L. Because this direction, this vector is how much? R2 bar minus R1 bar. That is the vector, because R1 bar and this is, if it is R2 bar minus R1 bar, the resultant of these two must give me R2 bar. So this vector will be R2 bar minus R1 bar, but if I want to find the direction, I need to divide with its magnitude, right? Now similarly, force because of this one will be gm1 m3 by L square along this direction, which is R3 bar minus R1 bar direction, that is R3 bar minus R1 bar by its magnitude. So this is the force because of the M2, this is the force because of the m3. Now I will be bringing m2 r2, I will be expanding and I will be bringing m2 r2 together and m3 r3 together, and m2 r1 m3 r1 together. So I will be getting these two things. Now m2 r2 bar plus m3 r3 bar, from this one m2 r2 bar plus m3 r3 bar, it will turn out to be minus m1 r1 bar. Why I am doing this is, if I do this, I can take m1 bar common and I can put it here. So when I substitute it and when I take that thing common, this thing common, then I will be getting m1 plus m2 plus m3. Now that is the net force. That is the net force on this one. Net force on this one in vector notation must be equal to minus m omega square r1 bar, minus m omega square r1 bar, because it will be performing circle with radius r1. This will be with radius r2. This will be with radius r3. So minus m omega square r1 bar. R1 bar, R1 bar, M1 and M1 will get cancelled. So from here you can get omega, you can get time period is 2 pi into root of L cube by G into M1 plus M2 plus M3, right?